I'm continuing an experiment that I started with the previous video where I tried to read my paper as we were preparing the final camera-ready version, and I thought that maybe people don't like actually reading and they might like to hear me read the paper out loud. I'll also scroll it behind me at the same time in case that's useful. If this process is also useful to you through these videos, especially if you have trouble reading PDFs, let me know and I'll continue to do it. Today's paper is Interactive Refinement of Cross-Lingual Word Embeddings. This is a paper by Michelle, Wojer, Ben, Leah, and myself. Cross-lingual word embeddings transfer knowledge between languages. Models trained on high-resource languages are applied to low-resource languages. We introduce Climb, an interactive system to quickly refine cross-lingual word embeddings for a given classification problem. First, Climb ranks words by their salience to a downstream task. Then, users mark similarity between keywords and their nearest neighbors in the embedding space. Finally, Climb updates the embeddings using the annotations. We evaluate Climb on identifying health-related text in 4 low-resource languages: Ilocano, Sinhalese, Tigrinya, and Uyghur. Embeddings refined by Climb capture more nuanced word semantics and have higher test accuracy than original embeddings. Climb often improves accuracy faster than active learning baselines and can easily be combined with active learning to improve results. Introduction. Modern text classification requires large labeled datasets and pre-trained word embeddings. However, scarcity of both labeled and unlabeled data holds back applications in low-resource languages. Cross-lingual word embeddings can bridge the gap by mapping words from different languages to a shared vector space. Using CLWE features, models trained in a high-resource language, like English, can predict labels for other languages. The success of CLWE relies on the domain and quality of training data. While these methods have impressive word translation accuracy, they are not tailored for downstream tasks such as text classification. We develop classifying interactively with multilingual embeddings, Climb for short, that efficiently specializes CLWE with human interaction. Given a pre-trained CLWE, a bilingual speaker in the loop reviews the nearest neighbor words. Climb capitalizes on the intuition that neighboring words in an ideal embedding space should have similar semantic attributes. In an analogy to geographic climbs, zones with distinctive meteorological features, we call areas in the embedding space where words share similar semantic features climbs. Our goal is to convert neighborhoods in the embedding space into classification climbs, with words that induce similar labels for a given classification task. For example, in the embedding for English-French sentiment analysis, positive sentiment words such as excellent, exceptional, and their French translations are together, while disappointing, lackluster, and their translations cluster together elsewhere. Curating words in the embedding space and refining climbs should help downstream classifiers. Let's now have a look at Figure 1, which shows this. A hypothetical topographic map of an English-French embedding space tailored for sentiment analysis. Dots are English words, and squares are French words. Positive sentiment words such as exceptional and génial are grouped in a climb, while negative sentiment words such as lackluster and décevant are grouped in another climb. The goal of these climbs is to improve text classification. Sadly, it cannot improve my French accent or pronunciation. Okay, continuing on. To find classification climbs, Climb uses loss gradients and downstream tasks to find keywords with high salience. Focusing on these keywords allows the user to most efficiently refine CLWE by marking their similarity or dissimilarity. After collecting annotations, Climb pulls similar words together and pushes dissimilar words apart, establishing desired climbs. Quickly deploying cross-lingual NLP systems is particularly salient in global health emergencies. So we evaluate Climb on a cross-lingual document classification task for 4 low-resource languages: Ilocano, Sinhalese, Tigrinya, and Uyghur. Using Climb, a bilingual speaker can significantly increase test accuracy on identifying health-related documents in less than an hour. We then compare Climb with an active learning baseline that asks the user to label target language documents. Climb is effective in this low resource setting. Under the same annotation time constraint, Climb often has higher accuracy. Furthermore, combining active learning with Climb increases accuracy even more. And the user-adapted model is competitive with a large, resource-hungry, multilingual transformer. Interactive neighborhood reshaping. This section introduces the interface designed to solicit human feedback on neighborhoods of CLWE and our keyword selection criterion. Suppose that we have two languages with vocabulary V1 and V2. Let E be a pre-trained CLWE matrix, where E of W is a vector representation of word type W in the joint vocabulary V, no subscript, which is the union of V1 and V2. Our goal is to help a bilingual novice, i.e. not a machine learning expert, improve the cross-lingual word embedding E for a downstream task through inspection of neighboring words. With limited annotation time, users cannot vet the entire vocabulary. Instead, we need to find a small salient subset of keywords whose embeddings, if vetted, would most improve a downstream task. For example, if the downstream task is sentiment analysis, our keyword set should include sentiment words such as good and bad. Prior work in active learning solicits keywords using information gain, but this cannot be applied to continuous embeddings. Lee et al. Suggests that the contribution of one dimension of a word embedding to the loss function can be approximated by the absolute value of its partial derivative, and therefore they use partial derivatives to visualize the behavior of neural models. However, rather than understanding the importance of individual dimensions, we want to compute salience for the entire word vector. Therefore, we extend their idea by defining the salience of a word embedding as the magnitude of the loss function's gradient. This score summarizes salience of all dimensions from a word embedding. Formally, let vector x, x1, x2 up to xn, be a document of n words with label y. Let L be the training loss function of the downstream model. We measure the local salience of word x of I in document x as the salience S of x is equal to the L2 norm of the gradient with respect to the word embeddings of the loss function of example x with label y. Equation 1 measures a local contribution of a token in one document, but we are interested in the global importance of a word type across many documents. To compute the global salience of a word type W, we add local salience scores of all occurrences of type W in a large label dataset X and multiply by the inverse document frequency IDF of W. So the salience for an individual word type is attenuated by the IDF times the sum of all of the individual example saliences. The IDF term is necessary because it discounts stop words with high document frequency. For example, the and of. These words are often irrelevant to the downstream task, but they have high total salience because they appear in many examples, some of which are salient. We sort word types based on equation 2 and choose the top S most salient words as a keyword set K. The hyperparameter S is the number of keywords displayed to the user, which also controls the length of a session. We limit S to 50 in experiments. For each keyword K, we want to collect a positive set, P subscript K, with semantically similar words and a negative set in subscript K with unrelated words. To specialize embeddings for a classification task, we ask the user to consider semantic similarity as inducing a similar label. For example, if the task is English French sentiment analysis, then good should be considered similar to excellent, and génial but dissimilar to bad and décevant. On the interface, keyword K is displayed with its nearest neighbors in the two languages, arranged in two columns, figure 2. The neighbors are the words W with embeddings EW closer to EK in cosine similarity. The number of displayed nearest neighbors can be adjusted as hyperparameters. For each nearest neighbor, the user can either press on the green check mark to add a positive neighbor to PK, or press on the red X to mark a negative neighbor to NK, or leave an uncertain neighbor alone. Users can also use the add word text box to add a new word not in the current neighbor list. The added word can then be marked as positive or negative. Section 3 explains how Climb refines the embeddings with the feedback sets P and N. The interface also provides a word concordance, a brief overview of the context where a word appears to disambiguate and clarify words. Users can click on any word to find example sentences. Let's take a look at figure 2 now. The Climb interface displays a keyword on top, while its nearest neighbors in the two languages appear in the columns below. A user can accept or reject each neighbor and add neighbors by typing them in the add word text boxes. They may also click on any word to read its context in the training set. Okay, section 3, fitting word embeddings to feedback. After receiving user annotations, Climb updates the embeddings to reflect their feedback. The algorithm reshapes the neighborhood so that words near a keyword share similar semantic attributes. Together, these embeddings form desired task-specific connections between words across languages. Our update equations are inspired by attract-repel, which fine-tunes word embeddings with synonym and antonym constraints. The objective in attract-repel pulls synonyms closer to and pushes antonyms further away from their nearest neighbors. This objective is useful for lexical resources like BabbleNet, with hundreds of thousands of linguistic constraints, but our pilot experiment suggests that the method is not suitable for smaller constraint sets. Since Climb is designed for low-resource languages, we optimize an objective that reshapes the neighborhood more drastically than attract-repel. For each keyword K, we collect a positive set PK and a negative set NK. To refine embeddings E with human feedback, we increase the similarity between K and each positive word, and decrease the similarity between K and each negative word in the set in subscript K. Formally, we minimize the following cost function, where the cost function for an embedding is the sum over all of our highlight words K, where we take the dot product of the embedding of the highlight word K, the negative example N, and subtract out the dot product of the embedding for word K and the positive examples, where EKEN measures the similarity between the keyword K and a negative word N, and EKEP measures the similarity between the keyword K and positive word P. Minimizing CF is equivalent to maximizing similarities of positive pairs while minimizing similarities of negative pairs. Topology preserving regularization. Prior embedding post-processing methods emphasize regularization to maintain the topology, or properties that should be preserved under transformations, of the embedding space. If the original CLWE brings certain translations together, those translated words should remain close after updating the embeddings. The topology also encodes important semantic information that should not be discarded. Therefore, we also include the following regularization term. So the regularizer is a sum over all words in the vocabulary that embedding hat shouldn't get too far away from the original embedding. Minimizing the regularizer prevents E from drifting too far away from the original embeddings, E hat. The final cost function combines the feedback cost, equation 3, and the regularizer, equation 4, where the hyperparameter lambda controls the strength of the regularizer. The updated embeddings enforce constraints from user feedback while preserving other structures from the original embeddings. After tuning in a pilot study, we set lambda to 1 and use the Atom optimizer with default hyperparameters. Section 4, Cross-Lingual Classification Experiments. We evaluate Climb on cross-lingual document classification. where we build a text classifier in a low-resource language using labeled data in a high-resource source language through CLWE. Our task identifies whether a document describes a medical emergency, useful for planning disaster relief. The source language is English, and the 4 low-resource target languages are Ilocano, Sinhalese, Tigrinya, and Uyghur. Our experiments confirm that a bilingual user can quickly improve test accuracy of cross-lingual models through CLIMB. Alternatively, we could also ask the bilingual annotator to improve the model by labeling more training documents in the target language. Therefore, we compare CLIMB to an active learning baseline that queries the user for document labels. CLIMB often improves the test accuracy faster. Then we combine CLIMB and active learning to show an even faster improvement of test accuracy. Finally, we experiment with refining the same set of keywords with multiple rounds of user intervention. The repeated sessions slightly improve test accuracy on average. Comparing active learning to CLIMB may seem unfair at first glance. In theory, document labeling only requires a target language knowledge, while CLIMB learns from a bilingual user. In practice, researchers who speak a high-resource language provide instructions to the annotator and answer their questions. So bilingual knowledge is usually required in document labeling for low-resource language development. Moreover, CLIMB is complementary to active learning, as combining them gives the highest accuracy across languages. Finally, we compare with XMLR, a state-of-the-art multilingual transformer. Despite using fewer resources, we train models on 572 English documents and test on 48 Ilocano documents, 58 Sinhalese documents, and 158 Tigrinya documents, and 94 Uyghur documents. The documents are extracted from Lorelei Language Packs, a multilingual collection of documents of emergencies with a public health component. To simplify the task, we consider a binary classification problem of detecting whether the documents are associated with medical needs. To balance the label distribution, we sample an equal number of negative examples. To transfer knowledge between languages, we build CLWE between English and each target language. We experiment with 2 methods to pre-train CLWE, train monolingual embeddings with Word2Vec, and align with CCA. Or train monolingual embeddings with fast text and align with RCSLS. The English embeddings are trained on Wikipedia, and the target language embeddings are trained on unlabeled documents from the Lorelei Language Packs. For alignment, we use the Small English Dictionary in each pack. Low-resource language speakers are hard to find, so we do not try all combinations of languages in CLWE. We use CCA embeddings for Tigrinya and Uyghur, or CSLS embeddings for Ilocano. Since Sinhalese speakers are easier to find, we experiment with both CLWE for Sinhalese. Our classifier is a convolutional neural network with the same architecture from Kim 2014. Each document is represented as a concatenation of word embeddings and passed through a convolutional layer. To preserve cross-lingual alignments, we freeze embeddings during training. The simple model is effective in low-resource cross-lingual settings. We minimize cross-entropy on the training set by running Atom with default hyperparameters for 30 epochs. All experiments use a GeForce GTX 1080 521 GPU and a 2.6 GHz AMD Opteron 4180 CPU processor. We use Upwork to hire participants who are fluent in both English and the target language. We hire 10 users for Ilocano and 25 users for Sinhalese. For additional case studies, we hire 1 worker for Tigrinya and Uyghur. Each user annotates the 50 most salient keywords, which takes less than an hour. For each keyword, we show 5 nearest neighbors for each language, which provides about 9 constraints for each keyword. After receiving feedback, we update the embeddings. We then evaluate the embeddings by retraining classifier using the new embeddings and computing its accuracy. For each set of embeddings, we train 10 models with different random seeds and report average test accuracy. We compare the test accuracy of a classifier trained on the updated embeddings against 2 baselines. The first baseline is a classifier trained on original embeddings, base in the figures. If we have access to a bilingual speaker, an alternative to using CLIMB is to annotate more training documents in the target language. Therefore, we also compare climb to uncertainty sampling, an active learning method that asks a user to label documents. We choose a set of 50 documents where model outputs have the highest entropy from a set of unlabeled target language documents and ask an annotator to label them as additional training documents. We then retrain a model on both the English training set and the 50 target language documents using the original embeddings. For each model, a human annotator labels 50 documents within 40 to 50 minutes. This can either be slower or take approximately the same time as an average climb session. Thus, any improvements in accuracy using climb are even more impressive given that active is no faster than climb. Finally, we explore combining active learning and climb. Document level and word level interactions are complementary, so using both may lead to higher accuracy. To keep the results comparable, we allocate half of the user interaction time to active learning and the other half to climb. Specifically, we use active learning to expand the training set with 25 target language documents, and we refine the embeddings by running climb on only 25 keywords. We then retrain a model using both the augmented training set and refined embeddings. Let's have a look at figure 3 now. Test accuracy of 4 methods on 4 target languages and 2 CLWE methods. Base uses the original CLWE and the original training set. Active uses the original CLWE and a training set augmented by active learning. We select and label 50 target language documents by uncertainty sampling and combine them with the source language training set. Climb uses the CLWE refined by climb and the original training set. A plus C uses the CLWE refined by climb and a training set augmented by active learning. The Sinhalese and Ilocano results are averaged over multiple users, while we only have one user for other languages. Each subcaption indicates the target language, embedding alignment, number of users, and average time per user. Climb has higher accuracy than active on 4 out of the 5 embeddings, and the combined A plus C model has the highest. Figure 3 compares the 4 methods described in the previous section. Climb is effective in this low resource setting. On all 4 target languages, the classifier that trains on embeddings refined by Climb has higher accuracy than the classifier that trains on the original embeddings. Climb reshapes embeddings in a way that helps classification. Climb also has higher accuracy than active learning for most users. The combined method has the highest accuracy. Active learning and Climb are complementary. Single sample t-tests confirm that Climb is significantly better than base, and A plus C is significantly better than active. We inspect the list of the 50 most salient keywords, which are identified as described in section 2.1. Most keywords have obvious connotations to our classification task of detecting medical emergencies, such as ambulance, hospitals, and disease. However, the list also contains some words that are unrelated to a medical emergency, including over and given. These words may be biases or artifacts from training data. To evaluate how feedback uncertainty changes accuracy, we vary the number of keywords and compare the test accuracy on Tigrinya and Uyghur datasets. For each keyword as from 1 to 50, we update the original embeddings using only the feedback on the top S keywords, and we evaluate each set of embeddings with test accuracy. For both languages, test accuracy generally increases with more annotation at the beginning of the session. Interestingly, test accuracy plateaus and slightly drops after reaching an optimal number of keywords, which is around 20 for Tigrinya and about 40 for Uyghur. One explanation is that the latter keywords are less salient, which causes the feedback to become less relevant. These redundant constraints hamper optimization and slightly hurt test accuracy. Let's take a look at figure 4. A comparison of test accuracy between sets of CLWE that differ in the number of keywords used to refine them. For Uyghur, pink, and Tigrinya, purple embeddings. The leftmost point corresponds to the base model in figure 3, while the rightmost point corresponds to the Climb model. Test accuracy generally improves with more feedback at the beginning, but slightly drops after reaching an optimal number of keywords. To understand how Climb updates the embeddings, we visualize changes in the neighborhoods of keywords with tsni. We inspect the user updates to the Sinhalese CCA embeddings. We confirm that positive neighbors are pulled closer and negative neighbors are pushed further away. The user marks epidemic and outbreak as similar to the keywords plague, and these words are closer after the updates. For the keyword ill, the user marks helpless as a negative neighbor because helpless can signal other types of situations and is more ambiguous for detecting a medical emergency. After the update, helpless is pushed away and disappears from the nearest neighbor of ill. However, a few positive neighbors are inadvertently pushed away, such as the Sinhalese translation for ill. The update algorithm tries to satisfy constraints for multiple keywords, so soft constraints may be overlooked. This motivates repeated climb sessions where the user can continue fixing errors. Okay, let's take a look at this figure 5. T-SNE visualization of embeddings before, left, and after climb updates. From one Sinhalese user study, we inspect two keywords, ill and plague, and their 5 closest neighbors in English, blue, and Sinhalese, green. The Sinhalese words are labeled with English translations. Shape denotes the type of feedback, plus for positive neighbors and X for negative neighbors. We investigate the effects of having a user complete multiple climb sessions. After the user finishes a session, we fit the embeddings to their feedback, produce a new vocabulary ranking, and update on the interface for the next session. We experiment on the Sinhalese dataset with CCA embeddings and ask 5 users to complete 3 sessions of 50 keywords. Average test accuracy increases with more sessions, but the improvement is marginal after the first session. By the end of 3 sessions, one user reaches 65.2 accuracy, a significant improvement over the 55.2 baseline. Let's take a look at figure 6. Progress of 5 Sinhalese users over 3 climb sessions. The largest increase in test accuracy occurs after the first session. The leftmost point is the base model from figure 3. Average accuracy for first session is not the same as figure 3 because only a subset of users are asked to complete 3 sessions. Contextualized embeddings based on multilingual transformers reach state-of-the-art in many tasks. So we compare climb with these models. Most existing models focus on high and mid-resource languages and do not cover low-resource languages. The only exception is the recently released XMLR, which covers Uyghur and Sinhalese. To compare with climb, we fine-tune XMLR for 3 epochs with Atom W, batch size of 16, and learning rate of 10 to the negative 5. Average accuracy is computed over 10 runs. For Uyghur, XMLR achieves 71.7 accuracy, which is lower than our A+C approach. This is impressive given that XMLR uses much more resources. 720 million parameters, 2.5 terabytes of multilingual common crawl data, and 500 GPUs. In contrast, the A+C model has 120,000 parameters and is built in less than 2 hours on a single GPU, including human interaction and model training. For Sinhalese, XMLR achieves 69.3 accuracy, which is higher than A+C. Common Crawl has much more Sinhalese words than Uyghur words. This aligns with our intuition. Climb is more useful in low-resource settings, while multilingual transformers are more appropriate for languages with more data. Further work can extend the interactive component of Climb to multilingual transformers. Ruda et al. Summarize previous CLWE methods. These methods learn from existing resources such as dictionaries, parallel text, and monolingual corpora. Therefore, success of these methods is largely determined by the availability and quality of training data. To improve the suitability of CLWE methods in low-resource settings, recent work focuses on learning without cross-lingual supervision and normalizing monolingual embeddings before alignment. In contrast, we design a human-in-the-loop system to effectively improve CLWE. Moreover, previous CLWE methods are heavily tuned for the intrinsic evaluation task of dictionary induction, sometimes to the detriment of downstream tasks. Our method is tailored for downstream tasks such as text classification. Prior approaches transfer knowledge with cross-lingual resources such as bilingual dictionaries, parallel text, labeled data from related languages, structural correspondences, multilingual topic models, machine translation, and CLWE. Our method instead brings a bilingual speaker in the loop to actively provide cross-lingual knowledge, which is more reliable in low-resource settings. Climb is inspired by human-in-the-loop systems that bridge language gaps. Brown and Grinter build an interactive translation platform to help refugee resettlement. Wan et al. Interactively align topic models across languages. A common solution to data scarcity is active learning, the framework in which the learner iteratively queries an oracle, often a human, to receive annotations on unlabeled data. Settles summarizes popular active learning methods. Most active learning methods solicit labels for training examples documents, while Climb asks for word-level annotation. Previous methods that use feature-level annotation are not applicable to neural networks and CLWE. Yuan et al. Propose an active learning strategy based on language modeling. Our keyword detection algorithm expands upon prior work in interpreting neural networks. Li et al. Uses the gradient of the objective function to linearly approximate salience of one dimension, which helps interpret and visualize word compositionality in neural networks. Their ideas are inspired by visual salience in computer vision. We further extend the idea to compute global salience of an entire word vector across a labeled dataset. Our update equations to modify prior work on specializing word embeddings, which are designed for improving word embeddings with a large lexical knowledge base. Farkey et al. Retrofit word embeddings to synonym constraints. Merksic et al. Expand the method by also fitting antonym relations. Mersic et al. Include both monolingual and cross-lingual constraints to improve CLWE. Glavis and Volik use a neural network to learn an external visualization specialization function that can generalize to words with no lexical constraints. Climb is an interactive system that enhances CLWE for a task asking a bilingual speaker for word-level similarity annotations. We test Climb on cross-lingual information triage and international health emergencies for 4 low-resource languages. Bilingual users can quickly improve a model with the help of Climb faster than an active learning baseline. Combining active learning with Climb further improves the system. Climb has a modular design with 3 components: keyword ranking, user interface, and embedding refinement. The keyword ranking and the embedding refinement modules build upon existing methods for interpreting neural networks and fine-tuning embeddings. Therefore, future advances in these areas may also improve Climb. Another line of future work is to investigate alternative user interfaces. For example, we could ask bilingual users to rank nearest neighbors or provide scalar grades instead of accepting and rejecting individual neighbors. We also explore a simple combination of active learning and Climb. Simultaneously applying both methods is better than using either alone. In the future, we plan to combine the 2 interactions by training a policy through reinforcement learning. So that's it. Congratulations if you made it this long into the paper. If you like this and you'd like me to keep doing it, let me know in the comments. I think it forces me to pay more attention to these papers. I don't know if it does anything for you, but if it does, do let me know and I will continue doing this.